Thank you. I am going to talk a little bit about projects we've been working on at the Naval Research Laboratory. And although I've given it kind of a long-winded name, in more practical terms, we've written a new LND, which I think will make it easier to add additional network protocols to Lustre. So the idea is that there's now another layer of software between LNet and whatever connection-oriented protocol you'd like to use. And because a lot of recent work in transport protocols has taken place outside of the kernel, I've tried to eliminate the need for LNet to use protocols that are only within the kernel. So a lot of newer things are implemented as a user library that you link against your application. So here's some of the reasons why we got started in this project in the first place. The basic problem we're trying to solve is that our deployed forces collect a lot of data in the field, and whatever they collect has to be sent to analysts to be examined for intelligence value. And whatever they come up with has to be sent back. The thing is, the analysts are nowhere close to where the data is being collected. In fact, every effort is made to keep them here in the U.S. So right away, you've got a problem of just network latency. And in addition to that, these networks have a tendency to be kind of congested, and congestion leads to packet loss. Now, if you're fortunate enough to have a terrestrial network to get you all the way from theater back to the analysts, then the latencies you're looking at are usually somewhere in the neighborhood of about 100 milliseconds round trip. And whenever I refer to latencies, I generally do this in round trip times just because I'm kind of a networking person. But the thing is, in most cases, you will not be lucky enough to have a terrestrial network the whole way. And oftentimes there's a satellite somewhere in the path. A satellite, or a single satellite, will add in the neighborhood of about 240 milliseconds to your round trip time, which is pretty significant. And I say add because there's still some terrestrial network in the path as well. So now that we've added another 240 milliseconds, we've also restricted the bandwidth even further. This is actually not a very friendly environment for reliable protocols, if for no other reason than the time that it takes to recover from a lost packet. So we think there are probably two good ways to go about tackling this problem. One is to pick a transport protocol that is well suited to this kind of environment and will make the most efficient use possible of the bandwidth available. The other approach would be to try limiting the amount of data that needs to be sent, and that's a little trickier. But to this end, we think that adding a file system into this scenario might be of some value. So currently, whatever data is collected, it all gets sent back wholesale. But if there's a file system available, then it should give the analyst an opportunity to kind of sift through the data before copying any of it. So for example, if you have a bunch of files, they can look through the files that are available. They can read the headers out of them and kind of pick and choose which files contain data that are of interest to them. Another good example is if you take the case of a file that contains video data. With a file system, you've got the ability to seek within a particular file. So now they can, for example, read a few frames, skip ahead so many frames, read a few more, and they don't actually have to move the entire contents to get something valuable out of it. That alone actually might be a compelling enough reason to add a file system into this environment. So I've mentioned that a lot of recent protocol development has happened outside of the kernel. In fact, the protocol we had in mind is one such example. We've been toying with the idea of using UDT for these kinds of networks. And we have some experience with it, and it's all been fairly positive. Some of the reasons I think that it is well suited to this environment I've listed here. First being that it uses an explicit negative acknowledgement. So in UDT, there are no duplicate acknowledgements. As soon as the recipient notices that there's something missing from the sequence numbers, it can report back immediately to the sender that these things are missing. And this reduces the amount of time to recover from lost data. What might be even more important is the congestion avoidance mechanism. So it's not really a new idea, but UDT does periodically send 2 of your data packets back to back. In other words, it'll send them as fast as the network interface will carry them. And they're marked so that when the recipient gets them, it knows to measure the time between these packets, and in so doing, it can figure out how fast they arrived. So it reports this information back to the sender, and for the next period, the sender can shape its traffic to that rate. And doing that will mostly avoid congestion or will avoid overfilling queues and network elements along the way, and mostly avoids congestion. All right, so now that we've got some way to avoid congestion, the window size, what we would normally call the congestion window, can be almost entirely determined by the round trip time, which gets measured. And so by doing this, there should always be enough data available to keep the pipe full. Now, I said it's almost entirely determined by round trip time. If there is packet loss, the window does get decreased ever so slightly. And this is important because it prevents retransmitted packets from themselves causing congestion and maintains stability in the algorithm. I've pointed out here that UDT allows you to provide your own congestion control algorithm. We haven't done that. I find the one that comes with it to be suitable. But if you choose to provide your own, it is a simple matter of implementing a few methods in a class, and you can override the ones that come with it. So despite the fact that we can use transport protocols that are outside of the kernel, of course, LND requires that some portion of it still be in the kernel. Although we've tried to offload the bulk of the work to the daemon process. Connection management, of course, and all the transport functions are handled outside of the kernel in this case. But now that we've split the implementation, we have to have some way of passing control and data back and forth between the two halves. And so we've chosen to use a character device, and that lets us do some really simple things like select an ioctal. With a little additional work, we can avoid copying message contents between the two halves. So we can memory map whatever pages are provided by LNet into the daemon's address space. So this is a quick overview, and really what you can see from this is that there is actually some overlap in bookkeeping duties. I think it's probably unavoidable, but the kernel, in addition to the daemon, also has to keep track of peers that are available and outstanding messages. But still, the heavy lifting is still done by the daemon process, and I should have included the transport functions on there. All right, so one possibly unusual aspect of the connection management here is that any one transport connection is expected to carry file system data in only one direction. And this really grew out of a quirk in UDT where we were having some reliability issues carrying data for long periods of time bidirectionally on the same connection. So it actually affected the design of our LND. So when the daemon process actually does have a connection to make, takes the same approach as some of the other LNDs and extracts an IP address from the NID. So the IP address, of course, is provided to the LNet kernel module and the network's parameter, just like always. But the interface that you provide there is not guaranteed to carry all of the traffic sourced by this LND. The daemon process does not bind to a particular interface for outbound connections. So this means that whatever routes you have installed and whatever routing policy you have in your system will actually determine the outbound interface and therefore the source IP address on those packets. So there's actually a chance that if you have a multi-homed host, you have some asymmetric movement of data amongst the network interfaces. I've pointed out that a little additional bookkeeping is required in the daemon where Lustre routing is involved. So we keep track of what peer is on the end of every connection. And if we get a message from a source NID that is not that peer, then of course that message has been routed. We keep track of that so that whenever we have return traffic, it's still the same simple destination NID lookup for the outbound messages. All right, so I don't want to spend too much time on the next two slides, but I think they do give a good overview of what's happening under the hood. So at the top of this diagram, the daemon process is actually waiting around in select, although I don't show it. So whenever LNet has a message to be sent, it provides it to the kernel half of our LND, and it wakes up the daemon process through a poll function. And when that happens, the daemon checks to see if the file descriptor is readable or writable. And in this case, it's writable, so it knows to call the transmit notify ioctl and get some information about the message to send. After it's done this, it can memory map the contents of the message. Once that's done, of course, you can call the transport protocol send function, and when the receiver has acknowledged receipt of the message, we can tell the kernel we're done through another ioctl and then unmap the buffers. The receive case is slightly more involved. So again, we're waiting around in select. But this time something arrives from the network instead of the kernel waking it up. And so the first thing we do is to call the transport function or transport protocol's receive function. And we only read enough data to get the LNet header. And after we've got it, we can call the receive start ioctl and provide that header to the kernel half, who passes it along to LNet. And at some later time, LNet will come back with buffers for this message to be received into. And from this point on, it's actually very similar to the transmit case. We receive the data directly into the buffers, tell the kernel we're done, and then unmap them. All right, so I've been talking about everything in terms of UDT so far. It's not actually necessary to use that protocol if you didn't want to. So we've provided an API that will, without too much effort, allow you to tack on other protocols. And the API kind of assumes that the protocols are connection-oriented. So if they aren't, it's only a little bit of extra work to make them look that way. But the API mostly has functions that look a lot like their sockets counterparts. So much so that the function prototypes are identical for a lot of them. And if you're using a protocol that has a sockets implementation, you can just provide pointers to things like connect and listen, send and receive. And we'll call those directly. Currently, it's necessary for all the peers in your network to use the same protocol because I haven't provided any way to negotiate that protocol. So whenever you start Lustre, you'll have to tell it which one to use, and all of the peers will have to agree on it. And just to make the point, I put together a small protocol backend that uses the Oracle RDS protocol, and it is not connection oriented, and it does actually use the have a sockets interface. All right, so here's kind of where things stand now. We've got things working in a rather controlled environment. So it's working at the lab. We're confident enough that we're willing to demonstrate it. And we've shown it with round-trip times between the client and the servers with up to 200 milliseconds. I've actually tested it up to 400 milliseconds, and it seems to work okay. Kind of the one sticky point here is that I don't yet have permission to hand out the source code. That's something we're working on. I'm guessing that within another month or so, that'll be resolved. All right, and here's where I think I'd like to go next. All of my testing so far really has really concentrated on validating correct behavior. And so I think we really should focus next on some performance testing and also make it a little bit easier to use. You can imagine that with the implementation split between the kernel and user space, some of the startup can be a little bit manual. All right, I've also listed a few things here that I think might be fun to do and probably not a whole lot of effort. But that's where things stand, and that's all I've got. Are there any questions?
As I see on use diagrams, you don't use ring buffers for messages from and to networks. It is have special reasons, or this is because this implementation is prototype?
I'm sorry.
Because you will be remove map and unmap calls if in case you will be use a ring buffer.
Okay, I'm not sure I quite follow. Yeah, there is some overhead associated with the map and unmap. That's certainly true.
Yes, but you can create some pre-allocated ring buffer with some area to put and get data from and to networks, network exchange, in other words. So you will have a single call for mapping this data to kernel space and removing from mapping. So just in setup and clean up code. This is just a performance question because in current diagrams you will be need 2 additional syscalls for each bucket. But if you create a ring buffer, you will be remove this.
Okay, yeah, so there certainly are some optimizations that could be made. And absolutely, for small messages especially, it may, if they're small enough, it might actually be more efficient simply to copy them through a read or write kind of system call instead of doing the mapping. I agree. For the use cases that we had in mind, we tend to have a lot of large messages, and I think that the overhead is at least for the way we're using it, justified. But that is a good point.
So have you effectively moved the worker thread pool to user space?
Well, there is a worker thread pool in user space.
Yeah, but I mean, many LNDs are structured that there's a worker thread pool that does the shoveling.
Right. Yeah. So the kernel half of this implementation is depressingly single-threaded.
Right. Okay.
Yeah.
By the way, Shadow, the buffer addresses are determined by whoever's using LNet. So the only reason you could use a ring buffer is if you use a ring buffer, you're forced to copy. So it's like was said, that would be an optimization for small messages.
Is the goal here to have a really high, over here.
Sorry.
There you
Talk.
go. Have a high bandwidth connection here, or is it just just to have a high bandwidth, high latency connection, or is it really for kind of these intermittent / slow connections?
Well, the reason we got started on it was because we have high latency, moderate bandwidth connections. So more it was to deal with the combination of latency and loss. The UDT protocol itself was actually designed to handle high bandwidth delay product networks in general. So, large latencies and high bandwidth.
So you are expecting to get some good performance out of this then?
I'm expecting to get better performance than we do now.
So first off, thanks for doing this work. You saved me some real problems. I've got a couple of protocols I want to work on that don't have KLNDs yet. I could only do them from user space. But the main question I want to ask is, when the time comes and you're able to secure permission to release this, how do the rest of us find out about that? Do you have plans on where you might announce it?
I suppose I guess the appropriate place would be to send email to the HPDD discuss list or something. Is that suitable?
Works for me.
Okay, done.
Okay. Eric Kinsey, thank you very much.